So in this video we want to develop the formula for differentiating exponential functions or functions of the form f of x equal a to the x. And our f of x equal a to the x is going to have the same conditions applied to it that were during a regular pre-calculus class. We don't want a to equal 1 because 1 to the x would just be 1, so we would actually have a constant. And then we want a to be greater than 0, so we want the base to be non-negative but also not equal to 1. And the claim is that the derivative d dx of a to the x is just equal to the natural log of the base times a to the x. So one way we could get at this would be simply to start off with our function f of x equals a to the x. And then what we could do is take the natural logarithm of both sides, because in the previous videos we identified how to take the derivative of a natural logarithm. So if I take the natural log of the left-hand side, I can then also take the natural log of the right-hand side. And then exponent rules for natural logarithms say that if we have a base to an exponent, the exponent can be pulled down into a coefficient position on the logarithm. So we can pull the exponent x down into the coefficient position, and now we have the natural log of f of x equaling x times the natural log of x. And then of course we want to recognize that this is just the product of two terms. So the natural log of a is actually just a constant. The natural log of a real number is just another real number. So I could also write this as the ln of a times x if I wanted to. So I have natural log of f of x equaling the natural log of a times x. And then what we could do is take the derivative of both sides. I could say, hey, let's take d dx, take the derivative of the left-hand side, and take d dx, the derivative of the right-hand side. And the derivative of the natural log of a times x is just going to be the natural log of a. So what we want to remember is that the natural log of a is just a constant. If we take d dx of a constant times x, we get the constant. So so d dx of pi times x would just equal pi. d dx of the natural log of a, which is just a constant times x, is just going to be the constant, the natural log of a. And then on the left-hand side, we have the derivative of a natural log, and we know that when we take d dx of the natural log of crap, we get the form 1 over crap times crap prime, and this is from the work that we've already done. So I'm going to get, if I take the derivative of the natural log of f of x, I'm going to get 1 over f of x times f prime of x. And notice what we're trying to figure out is what is the derivative of a to the x. So we're actually trying to figure out what does f prime of x equal if f of x equals a to the x. So all I need to do now is isolate f prime of x. I'm going to do that by multiplying both sides of this equation by f of x, which is going to isolate the f prime of x on the left-hand side. And of course the idea here is now I have the natural log of a times f of x, but I know what f of x is. F of x is a to the x. I'm going to replace the f of x here with a to the x, and now I have established a formula for finding the derivative of an exponential function. So if I can't remember the formula for the derivative of an exponential function, I could always go through this process of doing logarithmic differentiation, where I take the log of both sides, and then I use the fact that I know the derivative of the natural log has the form crap prime over crap, or f prime of x over f of x. And I could walk through and get the derivative that way. So you've got kind of two choices when you're taking the derivative of an exponential function. Well, one is to memorize the formula and apply it, which is fine. That's okay to do. Or if you can't memorize the formula, be able to apply logarithmic differentiation as a technique for finding the derivative, which is how we derived the formula.